Yeah,
Okay.
yeah.
Okay.
Yeah, sorry, there was some internet issue at my end, so I got a little delayed.
All right. It's okay. So, uh, Saksi, can you please?
Yes, sir.
Okay.
Good morning to one and all present here, and welcome on the second day of 1 week AICTCE sponsored faculty development program. Our today's keynote speakers are Monji Chaudhary from Microsoft Research India, and our second speaker is Amitva Das from Wipro AI Lab. Now, it's my privilege to welcome Chaudhary from Microsoft India, and he will be talking on multilingual zero-shot learning. Dr. Manjeet Chaudhary is a researcher in Microsoft Lab Research Lab India. His research interests cut across the area of linguistic cognition and computation. Currently, he is working on script and code mixing, especially in social media and web search. He is interested in developing core NLP techniques for identifying and processing code mixed text. He is also interested in studying the extent, distribution, and socio-linguistic factor influencing code mixing. He also worked on various NLP and information retrieval techniques for Indian languages. In the past, he has worked on computational musicology, language evolution, evolution on the structure of web search queries and complex network. So, may I request you, sir, kindly start your keynote presentation.
Thank you, Sakshi, and thanks to all the organizers for inviting me for this lecture. And good morning to all the participants. So, as you know, this is going to be a pretty long session because I think it's 3 hours. So, I have 3 hours for this. So, I would, encourage all of you to interact during the talk. So, please feel free to raise your hand or just pick up if you have questions, so that I'm not the only one who is speaking all the time. So and if you have comments also and all that are welcome too. Before I begin, I wanted to know how much has been covered in yesterday's lecture on word embeddings, because I saw there was a lecture on word embedding. Thodam, was it you who delivered it?
That was Dr. Ranbir Singh from IIT Guwahati.
Oh,
He-
I see.
yeah, so he started some bit of what to back and some introductions at the MLP level, how the word embeddings are used at the different levels of NLP task. So that was the very introductory kind of talk, uh, and something about
Okay, okay,
yes, yes, that much.
okay. Thank you. Thank you. I just wanted to make sure that I don't repeat much of what has been covered.
Yeah,
Okay.
sure. All
So
right.
I will share my presentation. Meanwhile, let me turn off my video so that the
Okay.
bandwidth is better.
Yeah.
Let me know when you are able to see the screen.
Yes, it's quite visible.
Okay. Yeah. So what I'm going to talk about is multilingual zero-shot learning. So let me begin by a much broader, picture of how NLP has been evolving over the years. So this is something which probably is known to all of you, but it's good to recap. So in 1950s to 1980s, oh, by the way, NLP is one of the oldest, sub branches of AI, and Turing test is almost, equivalent of what we call as language understanding today, or building of chatbots and so on, right? So it's almost synonymous to artificial intelligence, or you know, mm, so-called artificial general intelligence, and it's one of the hardest problems in AI we have been working on it for decades. There have been like waves of success and failures, uh, along with the AI winters and summers and so on. So it has a long history. Early days of NLP from 1950s to 1980s, it has been mostly rule-based systems. So it's like linguists would look at a language, write down the rules, and computer programmers would just take the rules and build systems. Slowly, in the next 4 or 5 decades, we have become more and more data driven. So 1990s is when the basic statistical machine learning techniques started getting used in NLP. Data sets were pretty small, and linguistic insights were still very important, especially when you were designing the features. The systems were as good as the features because data was not in plenty. Then in 2000s came the big data era. So we have this large scale supervised and semi supervised learning. Deep learning wasn't still there, but still, so when I say large scale, not large scale compared to today's scale. So at that time, compared to 1990s, 2000s saw a boom in data set sizes. And the machine learning algorithms were also getting better and more scalable. So features were still very important. As you know, for most classical algorithms, machine learning algorithms like SVMs or decision trees, one need to specify the features. So systems, the goodness of a system depended on how good the features were. Still, since we had a lot of data, we could live with some bad features. The system would automatically weed out the bad features and put more weight on the good features. So as long as you can define a union of all the features that you think are good, then
Excuse me, sir. Hello.
Manoj, your voice is breaking. Seems that there is.
sorry, yeah, there is some network issues at my end. So, but hopefully now you can, right?
Yes, yes.
I'll start presenting again.
Excuse me, sir.
Yes.
Yeah. Good morning, sir.
Good morning. Good morning. Tell
Sir,
me.
can you repeat? Can you repeat once the first slide?
Repeat what?
Yeah, which you have taught.
Yeah, I mean, this is just, there's no point of repeating this because most of you probably already know this. But I'm just trying to set up the context that now we have deep learning and multilingual zero-shot learning, which is the topic of this entire lecture. So don't worry, I haven't yet started. I'm going to start now. But
Okay.
the point is, with just a second. Yeah. Uh, Yeah, so the point is that we started from no data scenario and slowly moving to larger and larger data sets. And the linguistic insights that were required to build the systems have become less and less and less important. And in this whole process, we have been, I mean, people have been arguing, is linguistic insight important or not, and when is it important, and so on and so forth. So this is what this pendulum on this left side, right, shows, that we are sort of swinging between, data and linguistic insight, and it's mostly going towards data, and more data. Now, with that much of kind of a background in NLP, I mean, history of NLP. Let me tell you also that this landscape today is evolving very, very rapidly. So you see, BERT, if you don't know about BERT, don't worry. But I think most of you have heard about BERT, which is a word embedding system. Now, it came in 2018. And 2020 May, so just around 6-7 months ago, or maybe a little longer, came this GPT-3. And you see how the sizes of these models are growing. As the sizes of the models are growing, the accuracies are also growing. And GPT-3 uses only raw text It's a language model, so it uses only raw text corpus to generate language. But one very interesting thing about GPT-3 is it can support what is called zero shot task learning. So example could be like this, that you train GPT-3 model and you ask a question to it. The input is translate English to French and give this cheese as the example, and it will automatically be able to translate cheese to whatever it is in French. And if you give a few more examples, right? So instead of just saying translate English to French, you also give one example, sea otter and whatever it is in French, then it translates even better. Now, this is really, really amazing, because usually to translate, you would have to give pairs of this kind of word and their translation, so-called parallel corpus, in lots and lots of amounts, lot of data to train a system. But here you did not even train a system with lot of parallel corpus. It's just trained on English data, and somehow it's able to do it. And this is what kind of got everybody dumbfounded. Everybody's starting from media to scientists to uh, policymakers. Everybody is worrying, wow, oh my god, it's so powerful. Have we cracked NLP ultimately, and where are we going with all these? What are the ethical repercussions, and so on and so forth? Unfortunately, we won't be able to get into those questions. Those are also very interesting. How GPT-3 works, what are the ethical repercussions, and all that. But yeah, this is just how the performance varies, and but what we are going to focus today is on this zero-shot learning, and let me try to explain before we get into how to do it. Let me try to explain what does zero means here in zero-shot learning. So it's a very loosely used term, actually. So that's why don't get confused if you see various things being called zero-shot. So zero, supervised learning is where you have a lot of labeled data. Unsupervised learning is when you have no labeled data, and semi-supervised learning is when you have a mix of labeled and unlabeled data. So zero shot is kind of unsupervised learning. You don't have any labeled data for that particular task or class or language. Here is the main point which leads to confusion often. So people might refer to zero shot as a case where you haven't seen any example of a particular class. So for instance, you are let's say identifying animals, and you have quite a bit of examples of ducks and pigs and cats, but no example of tiger in your data, in your label data. But still, if you are able to identify tiger, your model, then you would say this is a zero shot learning. Here the zero shot is for the class. Similarly, the zero shot could be for task, like in the GPT-3 example. So it wasn't trained for translation, it wasn't trained for, let's say, sentiment, but it can actually kind of answer those questions. So it's zero shot for task. and or you might have trained it for some tasks but not this particular task, and if it works for that task, then it's zero shot for task. And finally, zero shot for language. So you might have data for task as well as unlabeled data for other languages but not my language. Let's say my language is Hindi, so I may not have any data for Hindi, but still if it works for Hindi, then I would say it's a zero shot across language. So in this talk we are going to talk about zero shot across languages. That's why it's called multilingual zero shot learning. Now, why this is important is, see, the resource distribution across world's languages is extremely skewed. Now, in this graph, on the x-axis, I am plotting how much unlabeled data is there across various languages. And on the y-axis, how much labeled data is there across languages. Each dot is a language. So no prize for guessing this, right? It's English, which has both very high amounts of unlabeled and labeled data. So in a recent study, last year we published this work in ACL. We were looking at how the resources across the world's languages are distributed. And when we looked at the graph, by the way, note that both the scales are logarithmic. That means, it's not that, this language is only, little better than these languages here, but it is actually 10 times better in both the axes, and 100 times better than these languages, and let's say 1,000 times better than these languages, and so on, because it's logarithmic, better in terms of resources. Now, when we looked at the graph, we said, okay, it looks like we can probably neatly classify this into 6 groups of languages, and we call them class 0 to class 5. And class 5 has all the resources. Languages like English and French will fall in class 5, and class 0 has no resources, no unlabeled data and no labeled data at all. Now, if you later I will get into which languages fall in class 5 and 0 and all that, and where the different Indian languages fall. But for now, it's important to note that a very large number of languages don't even have unlabeled data. Yet they might have some unlabeled data. And of course, some languages have neither unlabeled and labeled data. So data is a problem, and any solution that solves the data problem across languages, that would be fantastic. And that's where this multilingual zero shot is an excellent solution, because you no longer need labeled data for languages, for a large number of languages, and therefore you can build technologies much easily for languages like Bhojpuri or Assamese or Tamil, which we would not have been able to do it earlier. So how it works, this is a very high level picture. You basically train a word embedding model with raw text corpus from a bunch of languages, as many as 100 or 200 languages, and then you fine tune it, the embeddings. After the embedding layers, you have a fine tuning layer, or a task specific layer, which you fine tune with only labeled data for one language. Let's say only for sentiment, I want to do sentiment analysis. I fine tune it with only sentiment analysis data for English. And then suddenly it starts working for sentiment analysis of Hindi, French, Swahili, all languages. So it's almost a surprising thing. And it's so surprising that people have come up with this entire field called Birdology, which is the science of analyzing and understanding how BERT works. Because these neural nets are very opaque. We really don't know how things are, working inside them. Yet it worked, at least, as I described, it sounds almost like magic. You never trained it with any sentiment data for Hindi or French or Swahili, but only with English and only unlabeled corpora for Hindi, French, and Swahili. It starts working on all languages. And I thought this would be a very useful topic for to talk and discuss, especially in something in India or Indian context, because for Indian languages, there's a lot of promise in this multilingual zero shot learning. So what I'm going to do in this talk is I'll start with a primer to word embeddings. That's why I was asking how much has been covered. So I won't get into a lot of details because you already know probably the basic concepts. And then I will get into BERT-like systems, multilingual BERT-like systems, which are these multilingual word embeddings, and how the zero shot happens. So cross-lingual zero shot transfer. After that, so this probably I will cover in the first half, which is next 45 minutes or so. Then we'll take a break, and then we will get into some specific issues like evaluation and certain practical considerations, then some of the limitations and criticisms of these models, little bit of Bertology of how this works, and in the context of Indic languages and Indic NLP, what does it mean? So that's the plan. Any question, comment up to this?
Hello, sir. Sir, there are some questions in chat box by chat.
Can anybody read them out for me?
Yes, sir. Sir, the first question is that zero shot learning means that without training, we will directly predict the class level. Is it so?
It could mean that. Yeah, it could mean that. It could also mean that without training, you could generalize to a new task, like I said, or it could mean without training, without labeled training data, you generalize to a new language. So it is
And
used in a
the,
little loose way.
and the second one is that the zero shot learning support transfer learning.
Yes, so transfer learning and zero shot learning are very similar in many ways actually, but they are not equivalent because in transfer you might often talk about this is just a terminological mess, I would say. So in transfer, people typically talk about, let's say, transfer across domains. So, but you could also call it a zero shot learning because I don't have any data from that domain and now I'm able to do it for that domain. So that kind of thing, right? But the only difference is transfer learning never assumes zero shot. Means zero means no data, right? So in transfer learning, you can also do few shot. So it might be that you have a lot of data in a language uh, and very little data in another language, and you are going to transfer from language A to language B. So that need not be zero shot. You might have little bit of data, so then we will call it few shot. So that's the difference, I would say.
Okay, sir. Sir, that's only two questions was there.
Okay, okay. Okay, so let's get into the basics of word embeddings, which will be useful for appreciating rest of the talk. So as you know, right, one of the while deep learning revolutionized NLP, one of the stumbling block of introducing deep learning to NLP was how to encode words. Because unlike images or speech signals, which are continuous, so image is a continuous signal. Of course, in computer we discretize it, but nevertheless, it's a you could think of it as a real valued function. Each pixel is a number. Similarly, acoustic signals, waves are waveforms, and each point is a number, right? Frequency or energy or whatever number, depending on how you represent it. But in language, words are discrete symbols. So when you change a pixel little bit in an image, human eye won't be able to detect it. But if you change a letter in a language, in a sentence, the whole meaning might change, right? Um, I love Matt, I love cat. So just one letter changed, M became C, and the whole meaning changed. So that's a big challenge in representing language using neural networks, because neural networks are function approximators, real valued function approximators. So how did we solve it, right? Let's take an example. Uh, let's say we want to do sentiment analysis, and I have this thing, various words, various sentences, and their labels. So labels could be positive sentiment, negative sentiment, or neutral sentiment, and I want to solve this problem with a neural net. Now in supervised learning, one way could be, I I mean, the easiest way to think about how to represent words in this network is I have what is called a one hot encoding. So in one hot encoding, suppose my dictionary, my vocabulary has 10,000 words. So for every word, I have a particular location in my vector. So I have a vector which is 10,000 dimensional. So let's say this is the vector. Now, whenever the word is economic, let's say this particular location of the vector lights up, and everything else is zero. Whenever the word is growth, this particular location lights up and everything else is zero. So that's why it's one hot. At any given point of time, only one location of the vector is hot, which is the representation which is supposed to be for that word. Now, you could do it, train a sentiment analyzer using this kind of one hot representation. And it works
Excuse
also
me, sir.
if you had lots of, yes.
Excuse me, sir. In the last slide, are saying that if a word is representing something, only that particular vector is hot. But in the for the downward, nothing is there.
Sorry,
In the
what do you
last
mean by
slide,
downward? Yes, what do you mean by downward?
there is no hot. Yes,
Oh, for down.
yes,
You are asking for down, right? No, so there will be
yes, yes.
yeah. This is just an illustration. This is just an illustration. So yeah, this part of the vector, I mean, this is a pretty small part of the vector maybe, and it might be longer than that, or I mean, just take it as an illustration. So there should be something hot somewhere here in the down vector also.
Okay.
Yeah.
Should be now.
Okay.
That's I'm asking.
Yeah. There should be something. Yeah. So that's the one hot representation. Now, what happens is there are a couple of problems here. The first problem is if the number of words in a language is pretty high. So it could be around 100,000 words if you consider names and everything. Now, therefore, your input vector becomes very large. The second problem is it doesn't exploit the semantic and syntactic relations between words, right? So while cat and mat, by changing C to M, are very different. So there is no probably meaning connection between them. But consider a word economic and economical and economy and so on and so forth. They are somehow related. Or even if you consider the words like cat and dog and cow, they are related. So somehow these relations are not captured in a simple one hot encoding representation, right? So can we somehow kind of capture those? And if we can exploit that, we will probably get a better representation of the words. And that was the idea of basic word embeddings. So what people thought is instead of representing each word as a uh, one hot representation of the vector, let the vector representation be such that words which are similar in meaning are closer in the vector space. So I map each word to a point in a space, in an n-dimensional space, where two words are closer to each other if they are semantically close. But then the problem was, okay, conceptually it is nice, but how do you train such a model? How do you learn such a function? Because it's non-trivial, right? What should be the dimension? And there are so many words. Which words are closer? Why cat should be closer to cow and not, let's say, mat, and so on and so forth. So one idea was there is this linguistic theory of distributional semantics. It goes all the way back to 1957. And when I tell you that this is the kind of core idea behind word embeddings, don't get surprised. I mean, actually the basic idea existed long time back. So the idea is often quoted as follows: you shall know a word by a company it keeps. So essentially the meaning of words are always represented by, I mean, one way to look at the meanings is that they are represented by how the words occur. What are the other words around a given word, typically. So this was the idea used in at various points in computer science. People exploited this idea in various ways. So in the previous era, people used latent semantic analysis, or LSA, which is very similar. It actually is the same idea, but represented in different represented and computed in different way mathematically. So in word embedding, the idea was, well, I have this one hot encoding, and I pass it through a neural network and come up with a smaller vector. So this vector might be 1,000 dimension, 10,000 or 100,000 dimensional, but this vector might be much smaller, like 300 or 500 dimensional. And so some computations get done. After this, I basically have an output layer where the output layers could be, what are the words that appear around this particular word. So there are many models which you might have already learned, like CBOW, continuous bag of words, or skipgrams and all. I'm not getting into the details. These are like details of how exactly you model the context. So this is the word, and output is the context of the word, right? So what are the words typically that occur around XK? Now to compute this, like what are the words typically that typically occurs around XK, you just need a raw text corpus, right? You take a huge corpus, let's say Wikipedia of English, and take a word, let's say company, and you see all the sentences which is company and what are the words around company, and that will give you the training data for training. So this particular model is that of word2vec, and which you learned yesterday. And you probably would have seen these things also, that this has very nice properties, that words which are similar in meaning appear together, like dogs and cats, man, woman, and so on. Not only that, it has a nice it also captures the semantic relations very neatly. So for instance, the vector that is required to transform king to man is same as the vector that is required to transform from queen to woman. So the vector of king plus this vector gives you the vector of man, and vector of queen plus exactly the same vector gives you woman. So similarly, you have slow, slower, slowest, fast, faster, fastest. So slow to slower, fast to faster, long to longer, it's the same kind of vector. So it's not only capturing, words in the same space which are related, but it's also capturing how it is related, right? And it's so it is generalizing the meanings of the words very neatly into that space. Some observations are, this network can be used to, I mean, when I showed this network, I said you are taking the word and predicting its context. You could do the reverse, take the context and predict the word. So both ways it works. I already said only unlabeled text is required. So it's a kind of an unsupervised learning. Then if you know what language models are, and in fact, I think today there is a talk on language model, right? Later by Amitabha, or
Yes.
yeah, there is one. I don't know if it is today. So
Yeah.
you will see that language models are basically models which generate language and given some input. So in some sense, all these word embedding models are also language models, because given the word, it can generate its context, right? Or if you think of GPT-3, GPT-3 has given the sentences, a prefix of a sentence, a few words, it completes the sentence. Or given a sentence, it generates next few sentences. So these are what we call as language models. You already know about word2vec, fast text, which are some examples. Some good things about word embeddings are, it's task agnostic, in the sense that when you train the word embedding, you really did not train it for sentiment or train it for, let's say, natural language inferencing or part of speech tagging and so on and so forth, right? It's a very generic model. Now you can use it to solve any of these tasks. So that's why it's task agnostic. It's off the shelf. I mean, all these models are just available for many languages, including in many Indian languages. So you can just take it and use it for your purpose. It can be specifically tuned or trained for domains, genre, and languages. So this is important to note. So, if we use Wikipedia corpus, we'll get one kind of word embeddings for English, but that may not be appropriate for medical domain data, because Wikipedia is not rich with medical information, right? So you might go to another website or take data from medical domain and train something specifically for medicine. Or Wikipedia language is very different from that of social media. And if you want to take, train an embedding model to work on social media data well, you might just train it on tweets. So all these are possibilities, and people have been doing it, and all these things are available. Uh, what we need to do once we have trained the embedding is, for a task, we now need to do task specific fine tuning. So essentially we replace these, so let's say here where the one hot encoding of the word, it gives me the embedding here. After that, I was using, for training of this embedding, I was using this output layer, which was context, words in context. Now, once I've trained it, I just remove this layer and replace it by a much smaller, probably task specific layer, maybe a couple of layers of, just a feed forward network. What this task specific layer does is, given a sentence, let's say this is the best movie I have seen, so you have the word embedding of this here, then is here, the best, all the words, and then you somehow combine the word embedding of the entire sentence. You can do it as just a summation, or you can do it with convolution, many different ways actually by which you can combine. Once you combine, you have the embedding of the sentence. Then you can use that to predict the label. And for this, you just need to train this task specific layer. And for this, the good thing is you require a lot less data. If you were training from the beginning, if you did not have this task specific layer, and you were training, this entire network to predict the labels, you'd require a lot of label data. But now you need a lot less label data. So essentially, you have done a lot of unsupervised learning to learn how words are related. So now you need a very little label data to for the task, and still do pretty well for the task. So this is the primary advantage of using word embeddings. Now, so far so good, but still there are two problems in the model that I just described. One is, what about out of vocabulary words? So remember that to train a word embedding model, I need to start with one hot encodings. Now, one hot encodings will exist for words which I have seen in my corpus during the runtime, during the training time. Now, when I'm running it in the wild, a new word might come. Imagine name of people, right? Named entities, or in a morphological rich language, you might have seen the word, let's take an example from Hindi. So you might have seen a word like karenge, but you may not have seen the word karunga, because your data simply didn't have that. For instance, Wikipedia may not have any instance of karunga, or take a rarer verb and you may not have all its morphological variation. So you will always see out of vocabulary words, named entities, different morphological inflections and all, right? So how to learn good representation for these out of vocabulary words? This is one challenge. The second challenge is, often words have multiple meanings. So for instance, word bank, set, they all have so many different meanings. Now, as humans, when we look at the word in the context, we know what meaning it is. Okay, I was walking by the river bank. I went to the bank to take out some money. So these two banks are different. And what makes them different is the context. But in word embedding, or word to vec, each word has a particular embedding. So what would be the embedding of the bank? Should it be closer to river, or should it be closer to money? So and interestingly, most people kind of think that, okay, there are few words which have multiple meanings, but actually almost all words have multiple meanings. Take any word and it will have a large number of usage in any language. So it becomes a big challenge. So how to solve problem 1 and 2? Problem 1 was solved using a very standard, and not a, I would say, a classical method. It's not really a new method. It's called the byte pair encoding algorithm, where essentially the idea is we do not look at words as whole, but break words into subwords. And the why that helps, because subwords, I mean, when you see an unknown word, if the word is already in the corpus, you might use the whole word, information of the whole word. But if you see a new word, let's say karunga, which you may not have seen before, you might still break it into kar and unga. And unga you might have seen in another context, jaunga. So from there you can learn the meaning of unga and plug this to the meaning of unga in the case of karunga, and you are done, right? And that's how linguists do it. So linguists, do morphological analysis where they break word, a sentence in, sorry, a word into what are called morphemes and affixes, subparts, and each part has a meaning which gives the meaning to the whole word. So exactly this idea. But then morphological analysis is very, very expensive. You need to, get linguists who will sit down, write rules for the language. You have to ensure coverage and all this. So instead of that, people thought, okay, let's use some simple algorithm, statistical way of figuring out where the breaks are. And these are called, I mean, the algorithm that's used for most of this subwords splitting is called the byte pair encoding algorithm. I will very quickly go through the byte pair encoding algorithm, because later in the second half, when we talk of some of the limitations and criticism, this will be important. That's why I want to get into a little bit of detail of this. So imagine I have a corpus of words. And now I want to identify subwords. How do I do it? So let's say this is the corpus. I mean, here there are no word boundaries, so to say, but that's okay. I mean, with boundaries, you would have done it. I mean, nothing changes in the algorithm. What you do is, as a first step, you make each and every character as a separate subword. So A is a subword, B is a subword, C is a subword, and that's it here. Yeah, we don't have any more character. Now, by doing this, what are you achieving? If there are no other subwords, right? A new word can be at least broken down into the letters, individual letters or characters, and it can be processed, right? So if I see a new word in English, let's say AWP, which I have never seen before, and I'm not able to break it into any subwords, I will at least be able to break it into A, W, and P separately. And I would learn embedding for each subword, right? I will learn embedding for A, B, and C. So I can at least get an embedding for AWP and process it. It may or may not be optimal, but at least my system will not get stuck. But if we just stop at ABC and all, it won't be interesting. Each letter will be a subword, and we won't learn much meaningful things, because the meaning is in the words and not individual letters, or rather in the morphemes, root words. So what they try to do next is identify the most frequent bigram here. So in this, if you look at the bigrams, so AB is a bigram, BA is a bigram, and so on. And if you count, AB occurs 1, 2, 3, 4 times. And if you see BA, it occurs 1 times, 2 times, and that's it. And similarly, if you count all the other bigrams, you'll see AB is the most common bigram. So you actually include AB as a subword. So you include in your dictionary AB as a subword, and let's call it D for the time being. I mean, just I want to represent each subword by a unique symbol. So D. So now I replace all the occurrences of AB by D, and now I run the same algorithm again. I count which is the most common bigram, and I see DC is the most common bigram now. So DC becomes part of my corpus. So DC is essentially ABC, by the way, the trigram ABC. So that becomes my new word, a new subword, and now I replace it by E. So then I now look at it again, and what is the next most common bigram here? Unfortunately, there is nothing, right? Everything occurs only once. DE occurs once, EB occurs once, BE occurs once, everything. So I can't do any further compression, and I can stop here. There are also some other ways of stopping, right? If you take a entire corpus of English, you can actually go on. This process will go on and on and on. So there are two ways of stopping. One is you stop when you have had enough words. So you might say my max dictionary size can be 100,000. So when you hit 100,000, you will keep adding new and new stuff here in the dictionary, right? As the algorithm iteratively progresses. So once you have achieved 100,000 words, you stop. The other way of stopping is I will loop through this. I will stop when the frequency count of a new bigram falls below a certain threshold. So there are these multiple or different stopping criteria. So this is how we get subwords. Once we get subwords, everything, all the processes are now run on subwords and not words. So for instance, here reconstructing is broken down into rec, ons, and tructing. And this hash means it is actually a subword which actually joins with the previous word. So this is just a convention in which these things are represented within BERT-like systems. Is this clear? And are there any questions here before we move on to
Yes, sir.
the
Yes, sir.
next thing?
Sir, just in this slide, why the reconstruction is not break in re and construction or re and cons and then enter? Is there any process
Right.
of the
So
breaking?
yes. So once you have the dictionary, the
Yes, sir.
process of breaking is you try to do maximal matching. So suppose rec is already there. So you will try to read the word from left to right, right? And if you see that re is there, but rec is also there in my subword list, but reco is not there. So then I stop at rec and split there, and then again I start the algorithm at o. So
Okay,
on
means
is
the
there.
logic is that which the longest string we are getting in the dictionary.
Absolutely matching the longest string from left side
Okay, thanks, sir.
and
Good.
iteratively breaking it. So that's why it's important to note that it may not be broken into linguistically meaningful pieces. The linguistically meaningful breakup would be re and constructending, right? But it got broken in a weird way, and that's very common. But yet it works, and you don't need linguists. I mean, the whole point is how many linguists can you fire from the team? There is a very famous joke by Frederick Jelinek. He said, I think he was working in Bell Labs at that time, and he had this famous quote that every time we fired a linguist from the team, our accuracy improved by a certain number of points. Yeah. So essentially, it's the same process going on. So you are trying to remove linguistics as much as possible. We'll come back to linguistics. I mean, this was just a joke. Don't take it too seriously. But yeah, I mean, statistical processing helps because you might want to process it for hundreds of languages, and getting morphological analyzers built for all 100 languages will be impossible. Yeah. So these techniques really help. Any other question? Okay. So if none, then let's move to the second problem. So do you remember what the second problem was? The second problem is words are polysemous. They can have multiple meanings, and in different contexts they would have different meanings. So how do I make sure that I represent the right meaning in the right context? Now the problem for word2vec is given a word, you from based on the word form, you learn just one embedding for it. Ideally, you should learn the word should not have an embedding. The embedding should be of a word in the context. So bank used in 10 different sentences should have 10 different embedding. So this is the idea which motivated this whole paradigm of transformer based word embeddings, including BERT and Robota and so on, right? Even GPT-3 and all are transformer based architectures. So the transformer based architecture, it's I mean, I don't know how many of you are already familiar with the internals, but the internals are little too complex to get in here. It will take too much of time, but I will give you a high level idea. So a transformer has two parts. One is an encoder and one is a decoder. Transformer is like LSTMs, right? So it's a neural architecture, like LSTM is a neural architecture, or an RNN is a neural architecture. So similarly, transformer is a neural architecture. So one particular transformer has an encoder part and a decoder part. Now, usually we stack a bunch of transformers one on top of other. We'll get into the details like internals later, but let's look at the bigger picture first. So suppose you want to kind of represent the sentence "मैं प्रकृति का आनंद लेती हूँ" in Hindi. So what you do is you take the entire sentence, each word here, right? मैं प्रकृति का आनंद लेती हूँ, all the words together, and try to first you get their word embeddings, word to vec embeddings, and then with the word to vec embeddings you add something called positional encoding, because here we will represent the entire thing as a bag, but since we don't want a bag, we want the word order to be preserved. So I want to add a positional embedding. So the positional embedding is also pretty complex, but a simple way to think about it, I mean, simple but incorrect way to think about it is, let's say "मैं" is the positional embedding of "मैं" is 1, "prakriti" is 2, "ka" is 3, "anand" is 4, and so on. So it just tells me where the word actually appeared in the sentence. So I add the positional embedding of the word along with the word to vec of the word. So this gives me one entire embedding for the sentence. So basically I concatenate these embeddings now. So my embedding for "मैं" and its positional embedding, then embedding for "prakriti" and its positional embedding, uh, added to its positional embedding, embedding of "ka" added to its positional embedding, and so on. And I will join each of them. I will concatenate, and that gives me the vector of a entire sentence. That whole vector goes in here. There is something called attention that happens here, which I will talk in little more detail in the next slide. And and there is a feed forward network, after which it generates a representation, a new vector. So here went in a vector, right? A long vector of the entire sentence. A similar length vector is created here after the computation. Then the same kind of computation happens in the second encoder. The only thing that differs between the encoders is probably the weights, because the weights are learned. So weights in this feed forward network, or the attention weights, because these are learned during the training process. So it goes through this, then it comes out, then goes through this, and so on and so forth. You can stack as many encoders as you want. So it is encoding. Then the next step is decoding, because without a decoder you cannot train. So suppose we want to decode this sentence into English. So basically I'm training a translator from Hindi to English. So the decoder, what it does is it takes the final output of the final encoder layer, and it goes into this decoder. So decoder again has similar thing. It has these attention layers followed by feed forward layer, and it generates a decoded sequence. Then this decoder takes that decoded vector and generates one more, and this one takes the same vector and generates one more, and so on. By the way, at every step, it not only takes the decoded vector, but it also takes the encoder vector. So it's because of the what is called the recency effect. So what happens is, as the decoder, it keeps decoding, the vector here would have already lost a lot of information of the original encoding, right? So at every step you also give it the original encoding. So the sentence meaning, which is captured in this original encoding, is also available to this decoder at every step. And the output of the final decoder is finally decoded using the typical softmax kind of a thing. How I mean, you get back the words from the decoded vector. So and you can basically now decode it into English and get this. So this is the high level picture. Internally, there are lots of details of how the encoders and decoders work. Like I said, I don't have time for this here. But one thing I want to mention here is Transformers has two great not advantage, I would say two great innovations. The first innovation is representing the whole sentence as a single unit, right? As a vector, instead of each word separately. So the word embeddings are encoded in the context of the vectors. The other thing, in context of the other words. And the other thing is attention, which actually further strengthens this context, especially long distance context. So what happens in the attention is, when you are, it's called self attention. So when you are generating the, you had an input vector. So when you are encoding it further, you are actually, for each word, you are looking at these, there are these attention heads which are looking at the same sentence, all the other words. That's why it's called self attention. It's paying attention to the other words in itself. So it will look at the animal didn't cross, and of course there's a matrix multiplication computation, those weights are learnt and so on. So you can imagine at the end of the process, after all the multiplications and normalization, etc., it will be actually paying a lot of attention to, let's say, some of the words like the and animal and street and itself in the but not all the words equally. And this makes sense, because if you see the sentence, the animal didn't cross the street because it was too tired. So what is it referring to? So it is referring to probably the animal, and therefore ideally this it should pay more attention to the animal. But if I said the animal didn't cross the street because it was sorry, it was too wide here. If I said the animal didn't cross the street because it was too tired, then it would refer to the animal. But if it is too wide, then it would refer to street. So accordingly, it will pay different attention to different words. So this is one important innovation in the transformers. Now, what happens is, typically you take the here I took an example of transformer training using translation, but it need not be translation. It could be the same language. So you can say मैं प्रकृति का आनंद लेती हूँ as the input to the encoders, and the decoded output could be also मैं प्रकृति का आनंद लेती हूँ, but you might mask one of the words. So this gives us the masked language models. So in masked language modeling, what happens is, let's say I say language, and mask refers to predicting mask word given the surrounding context. So this is my input, and the machine is supposed to give the output. Language model refers to predicting next word given the surrounding context, or predicting masked word given the surrounding context, right? So you could use the same language corpus, and therefore in an unsupervised way you can train these models. Once you have trained these, right, for a BERT like system, you really do not use the decoder anymore. So the final output of the encoder becomes the encoding of your sentence. Whereas in some other models like GPT-2 and so on, you do not use the encoders, you only use the decoders, because you want to generate the sentence, complete the sentence. So all of them use transformers, but in slightly different ways. Okay, let me stop here for a moment if you have questions. If not, I will quickly cover two more points, few more points, and then we'll take a break. So why these transformers are, I mean, people are so crazy about transformers and everybody is talking about them, is because if you look at, some of these language understanding tasks. So in this table, each of these data sets refer to a language understanding task, and together all these data sets is called the glue. Glue is generalized language understanding evaluation. And there are a whole bunch of numbers. Don't look at all of them. Just look at average over all these data sets, right? So the last column, average. So what happens is, in pre-OpenAI SOTA, so these were also neural network based results, you had 74% accuracy as average. And, a lot of things like BiLSTMs, Elmo, attention, even some parts of, attention was, the idea of attention was older. So people used it earlier as well. And in OpenAI GPT initial model, like GPT-1 model, if you look at that, with all that also you couldn't go very far. So 74 became 75. But with BERT, you get so high performance like 82. And the 82 from 74 is what? Good 8% improvement. So this is a huge improvement for this kind of very hard tasks, right? And that's why, people say that these models have revolutionized NLP. Now, if you're wondering what is BERT base and BERT large, I think BERT large uses, I always forget the numbers, 12 layers or 24 layers, probably 12 layers of encoder decoder. Yeah, and BERT base probably use 6 layers. something like that. So it's just the number of layers. Okay. So essentially what is happening is, as with time, your state of the art grows, right? So typically in a hard problem, in any hard problem in any field, you typically get this kind of a curve. So your accuracy initially increases with new technology fast and then slowly saturates. But only when a new technology comes, right, suddenly you get a jump. And BERT was that kind of a technology, where suddenly something came which gave you a big jump there. And of course, this we talked about earlier, as how newer and newer models are coming every other day. And we also have BERTs of, not only one single BERT for English or many languages, but we also have, medical BERT, we have, social BERT, and so on and so forth. So this is probably a good point to take a break. If there are any questions so far, I can take one or two, and then we will take a 15 minutes break and again join at 10:45. Any questions?
Tindukuri Mallikarjuna, please ask the question. You have typed at the chat box.
Sir, good morning, sir.
Morning.
Hello. Hello. Sir, BERT is a word
Yes.
embedding model or a pre-trained model which supports transfer learning. Which one is correct between these two?
That's a great question, actually. Thank you for asking this. Actually, both are same. Most people confuse. So, word embedding model, language, and pre-trained language model means exactly the same. It's called pre-trained because you have two parts. Remember that thing I talked about, pre-training and fine-tuning. These are two very important concepts that one must actually remember all the time. So, here, right? Um, so initially you train the word to wake or BERT or anything using this kind of an architecture, where you have this encoder part. This part is the first part is encoder, and then you have a decoder part. Then after that you might throw the decoder away. So once you throw the decoder away, you just keep this part, which becomes your pre-trained embedding model. Pre-trained because you have already trained it. And now for a task, you fine tune task specific layers. So when you are saying, pre-training, you mean pre-training versus fine-tuning. And when you are saying word embedding, it's just this part, word embedding, but it's exactly the same model. And when you are saying language model, it's also the same thing, because essentially language models look at the context and try to, you know, generate the next word or the word in between given the context, right? So all these three things in this case of BERT kind of models mean pretty much the same thing.
So BERT supports two kinds of things for generating the word embeddings as well as using as a pre-trained model. Am I correct, sir?
Yes, yes.
Okay, sir. Thank you.
Yeah.
Thank you. Sir, one more question is, while working with the BERT pre-trained model, so am I go for some other kind of word embeddings other than BERT, like glow vectors? Hello.
Yeah. Go ahead.
Sir, while working with the BERT pre-trained model, so am I use other kind of word embedding models like glow vectors while feeding the input to
So
the BERT model?
yeah, that I also mentioned
Hello.